Hi, everybody. My name is Khawaja. I'm the co-founder and CEO at Momento. Super excited to be here today with Manju. Manju, welcome to the show. Would love to hear a little bit about your background and a quick introduction on you.
Thank you, Khawaja. Really excited to be here. I'm Manju Rajashkhar. I'm VP of Engineering at Etsy. I lead two groups there. One is around enabling machine learning across Etsy, and the other group is personalization engine. Prior to Etsy, I started a company called Blackbird. We did multimodal deep learning. We started out in 2013 when deep learning was just getting started. So a lot of work that we did was providing search and recommendation as a service using all of the recent advances that were coming out in deep learning at that time. Before that, I was fairly early at Twitter. I joined when there were around 100 of us, and the traffic grew from 50 million to 200 million active users to the span of a year and a half. I was there. I was responsible for building the caching systems to fairly well-known open source pieces that we built inside Twitter during that time. One of them is called Twem Cached, and the other is Twem Proxy. I'm very passionate about building large scale systems, distributed systems, machine learning, search systems. I'm also very passionate about building high performing teams and coaching leaders. I think that those also bring me a lot of joy.
That is awesome. So is it fair to say, Manju, that you were doing AI and ML before it was cool?
Once it started out in 2013, once the deep learning came about, everyone wanted to do it. I think we were just lucky to have all of those advances come in, and it became really exciting to work on it. Because before that, it was just really hard to like build really performant models, and it kind of got easier after that.
So you've done a lot of work on search, right? Clearly, for the rest of us, we're still new to this space. Um, just some basics. What's an index?
Hmm. So I'm sure we've all come across it in our day to day. If you've ever picked up a book, the first thing you probably do is go to the table of contents, right? And the table of contents would tell you which sections of the book is speaking about a particular topic. Now that table of contents is actually an index, or more concretely called as the forward index, because you go in the forward direction. You go from the table of index all the way to the different chapters that contain that particular topic. If you've ever gone to a site, there's something called as a site navigation, usually a nav bar at the very top. And now that's another example of a forward index, because it helps you navigate the site and tells you like, oh, if you really you want to do returns, go to the return section. You want a customer support, go to this particular section. Now, if you go to the back of the book, there is another index called appendix. Now that has words, and it has which pages in the book have those words appearing. So that index is the reverse index. And so there are like these two kinds of indexes, but index really is anything that lets you get to the information really quickly. And these both things allow you to get to the information really quickly, but the same pieces keep appearing in different parts of computer systems. It helps you appear in other domains like finance industry, where you have an index tracker, which allows you to go from an index to all of the tickers that are part of those indexes.
Awesome. That's a very cohesive way to explain. For me, at least, it's a little clearer what an index is, but just showing how much of a discovery and navigation is powered by an index makes it a lot more real.
Yeah.
Personally, the way you put it, because I never thought of a site navigation bar as an index, and I think it captures the essence of not only letting me look stuff up, but also powering my journey and directing it towards discovery of the site, of the products. And I am really curious, there's different types of indexes and new ones are coming out, but the one that has been really common has been an inverted index. So love to hear your version of what you think an inverted index is, and we'll follow up with some of the other indexes shortly after that.
Yeah. Yeah. So we talked about indexes. We talked about the forward index, which was the table of contents. And we talked about the reverse index, which is the appendix at the end of the book. Now, inverted index is really the reverse index. So where you go from words to which pages in the book that has those words. And the same analog in search appears like you go from words and which websites have those words, right? So let's say you go to Google and you type in CNN, right? You probably want the Wikipedia page for CNN to come in because it's talking about CNN and it has those words. And you also want the CNN website to show up on the search results too, right? But you probably rarely would a BBC now website would show up on the results because the CNN word doesn't occur that much on the BBC website, right? And so that's a example of a reverse index, which we commonly known as inverted index.
Got it. And is this, in the modern technology world, I assume this is what like Lucene or Solar or OpenSearch, Elasticsearch, would you put those in the category of the traditional inverted index?
Mhm. Or traditionally we call that as information retrieval. Or now the classical way of doing information retrieval is the inverted index. And it's the basis for all of the information retrieval that would happen.
Got it. And now we're seeing this new form of neural index,
Mhm.
or a vector-based index or an embedding-based index. Curious to hear what your take is on what term you like to use and your definition for this particular type of index.
Yeah. So we've talked about like words and we talked about indexes that take you from the words to the documents, and take you from the words to the websites that have those words showing up. But not all input is words. Like let's say you're at a museum and you're looking at a painting and you really like that painting and you want to have a painting like that for your home. Now that is very hard it's like almost impossible to describe it in words, right? And the best way to find that painting is probably using an image of that painting, right? And so that's search by image. So we're moving into this world, especially that has happened over the last few years, is a lot of the input to the search systems, a lot of the way that people are expressing what they want is not necessarily in terms of words. You have images, you have videos, you have combination of images and videos and things like that. So we needed a different encoding or a different representation of that input. Now that representation over has been the name for that as that we've all kind of aligned on is called as an embedding. And an embedding is just an abstract encoding for the for whatever your input is. So you can take words, you can convert them into an embedding. You can take images, you can convert them to an embedding. You can take a combination of those and convert them into an embedding. And that embedding turns out to be a vector, which is why you said a vectored index, or those embeddings is just also called as just an embedding index. And the neural index is another word for the same thing. But the index is instead of trying to search from words to documents, now you're just searching over embeddings. And the index is the index of embeddings.
Got it. So for everybody else out there, and for me, I would love to, so I think I get what a neural or a vector index is. You talked about embeddings. So let's talk a little bit about what is typically the format of an embedding. You said you could represent an image with it, you could represent text with it. What does an embedding look like?
Um, yeah, no, maybe I can go back to like the basics, like what embedding is. Like we're all familiar with the number line. And so a number line is you have numbers going all the way from 0 to keep growing on the right side, and you have numbers growing on the left side. Now you can imagine those numbers as just an embedding, but in a single dimensional space, because the dimension is just one. And so what the embedding space allows us to do is that if two numbers are close to each other, then we kind of say that they're similar. And if they're away from each other, then they are dissimilar. So in a number line, numbers like 0 and 1, or numbers like 10 and 11, or numbers like -12 and -13 are all close to each other. So they're kind of related. But numbers like -10,000 and 0 are really far away from each other. And so they might be dissimilar. Now you can expand that a little bit and you say, well, maybe my embeddings are just two numbers together. So you would go from a number line to a 2D representation where you have the x-axis and the y-axis, and you have these four quadrants, right? So in this space, you can see everything that appears in the positive quadrant, right? Which is all the positive numbers, all positive X numbers, all positive Y numbers. They're like closer to each other. So that's a two-dimensional embedding. You can extend that to 3 dimensions. You can say that to 4 dimensions. You can extend that to 5 or more. At 5 or more, it's hard to imagine what's really happening and what's close or far away from each other. So
Yeah.
embeddings are just these like collection of numbers, and you call them and so there are two things that are representing like which dimension an embedding exists, and what is the function that we use to find whether embeddings are similar or not. And in this like really, really high dimensional space that is hard to imagine, where the embeddings appear, and that's the embedding space. So the
Got it.
goal for constructing an embedding is to take anything and converting it to that that vector or that collection of numbers.
That makes sense. So in the two-dimensional example, would you do like a Cartesian distance to say how similar or dissimilar an object is if you wanted something that is more fine-grained than which quadrant you're in?
Exactly, exactly.
And
And
Mhm.
let's say if you were in a three-dimensional space, you could project, or you could take a slice of the three-dimensional object. Let's say you had a spear in
Yeah.
the three-dimensional, and you ran in it. You took a samurai sword and you sliced it, and you
Right.
projected it all the way on 2D, and that's the same representation of an embedding, but in a different space. And you can see how what is similar and dissimilar really depends on which space you are in. So two objects that are far away on a sphere could be really close to each other on a 2D space, but really far away on a 3D space.
Wow. All right. So this is really blowing my mind. So now what we learned is you mentioned there's a function that can generate the embedding. So I let's say I've got an image, I feed it into this function, it returns to me an embedding, which, as you explained, is a collection of numbers. And then I can search for things that are similar across that hyperdimensional number. So if I take another image, generate the embedding for that, I can go in and say, what are the images that look similar to this particular embedding in across these dimensions that I've generated them in?
Exactly. And that is searching over the embeddings. And that's where neural index really helps, because it allows you to get to those embeddings really quickly.
Awesome. So now we talked about two types of indexes. It's really difficult to choose. I'm curious if there are attributes of neural indexes that make them better for some sort of searches. Other than the fact that sure there's images, you can't do that necessarily with an inverted index, but even in the text form, I'm curious if there are things that a neural index can do better than an inverted index and vice versa.
Yeah. That's a really great question. And what's important to see that this is kind of the design space, right? The different ways of getting information. And with any kind of computer science problem, you'll always have trade-offs
Mhm.
and capabilities, right? And so the trade-offs between an inverted index and a neural index is, one is around latency and cost, and the other is around capabilities and accuracy, right? So we've had decades of research and production and expertise with like scaling inverted indexes, which is why like if you go to Google and you type in something, you get your answers really, really quickly, because at the core, it's using an inverted index. But go to ChatGPT and ask the same question. It's going to take some time to like give you those answers, because at the core, it's using a neural index. So there are those, and with so there's a latency aspect for it, and because of the years of research, inverted indexes are also super cheap to run. While if you want to run neural indexes, depending on the size of the space that you're searching over, that might be so expensive and sometimes even prohibitively impossible to even do. Right. So that's one. The other is the question of capabilities. So if something is cheaper to do, and let's say an inverted index is cheaper to do and a neural index doesn't give you better answers than the inverted index, then there's no net new value added by the neural index, right?
Mm.
So So if I type in CNN, an inverted index could just give you, here is CNN, right? If I type woodworking, then inverted index would give you, here's a Wikipedia page for woodworking. And here are some items that you can buy for woodworking, right? And so inverted index really shines there. But then, but neural indexes are really great at like complex natural questions, right? And so how do I get how do I get started doing woodworking? Now that's a question that typically inverted index are not, designed to solve. Like and so neural indexes can solve a Q&A type of question really well, right? So they're each like experts in a kind of question that you've been asking.
Got it. Got it. And then how do I pick? Or is the answer that I need both depending on the app? I'm curious if there's applications you see in which one works better than the other.
If given a query, we can see which one is really good at answering the question, then you can just route the query to the appropriate index. But in a world, let's say you don't know which one is really good at answering, you can ask all of them the question, and you could use some sort of a quorum to figure out, if two people say this is the answer, it most likely is the answer. And you can use those kinds of techniques to to get your results to be more precise.
Got it. So what I'm hearing is the query comes in, you triage it, decide if it's really just an inverted index query or a neural index query. If I give you an image, a neural index query. But if I give you some text, it might be unclear whether it's an inverted or a neural, and you might want to run it on both and then combine the results. I think by quorum, what you're talking about is if both of them return a particular result, that's got to go to the top of my ranked results. And then are there heuristics that you use for things that are less obvious where, a neural index gives you some results, inverted index gives you completely different results? How would you kind of rank them against each other?
Yeah, you go back to the foundations of machine learning, right? You deploy the system, you for for a for an initial period of time, you get answers from both and see how the users are interacting. If for certain queries, user is interacting more with the results that are coming from inverted index versus neural index, then the system can learn those things. And if for other kinds of queries, if it's interacting with the neural index results, then the system can learn those things. Now you can layer in trade-offs around cost, latency, right? And how can you, like, the system can constantly be learning. And now you have this self-learning system that is deployed.
That is awesome. I, I really appreciate this conversation because I feel like you've really crisply laid out some really complex concepts. Um, and just making this whole AI ML thing a little bit more real with a very specific problem around semantic searching. Um, I super excited to hear other additional conversations with you. Are you presenting this anywhere? Are there venues that you're going to be talking about this anytime soon?
Yeah, no, I'm talking about designing, about like how can we design a really flexible search system in this like new world where we have like embeddings that are really accessible to a lot of us at MoCon, which is happening in 2 weeks from now on August 3rd in Seattle.
Right. Super excited to see you there, and no pressure on your talk, and I'm sure it'll be great. Thank you again for this podcast, and thank you for taking the time to present at MoCon as well.
Thank you. And thanks for having me here.